All right, welcome back. So today what we're going to talk about is how we can use the ideas of integration and Riemann sums to turn certain questions into questions about integration that we can then solve using the fundamental theorem of calculus. And this is kind of illustrate how a lot of these applications of integration are going to go. We will start by taking a problem. We will show that this problem can be reduced to a limit of Riemann sums. We will conclude that nobody in their right mind wants to actually compute this limit of Riemann sums directly by using definitions of limits, but we will observe that a limit of Riemann sums can actually be interpreted as a definite integral. And because it can be interpreted as a definite integral, we can just write down that definite integral and solve it using the fundamental theorem. And therefore, we can actually, we start with the Riemann sums and the limit of them in our problem, but the goal is to move away from that and be able to just solve it using a definite integral. So the first example of this is one which I think is sort of more or less straightforward to understand what's going on. And this is about areas between curves. And I want to start with the following basic problem. So let's suppose that on an interval a to b, we have f of x bigger than or equal to g of x. And we want to know what is the area enclosed by x equals a, x equals b, y equals f of x, and y equals g of x. Well, the answer is, let's try to write down a Riemann sum and then see what the integral would be. Now, you can probably kind of guess what the answer is going to be here, but let's show how you actually figure this out. So, making a little bit of a sketch here, and, I'm just kind of drawing an arbitrary situation here. I'm not saying that all situations are going to look just like this. So here's my x equals a and x equals b. Those are going to give me vertical lines. And then let's say here's my f of x. I don't care what happens to it outside of this interval. And here's my g of x, let's say. How would I find the areas? Well, the simple answer to finding the areas is I'm going to approximate the area of this region by rectangles. I mean, it's kind of what we did when we first started thinking about the Riemann integral in the first place. The only difference was that for that Riemann integral, we just thought about areas under curves and above the y-axis. The difference now is that on the bottom, I have some different function. But what I can do to do the approximation is I can still say, okay, let's break up this interval into several pieces, and then on each piece we'll draw a rectangle. The top of the rectangle is going to get determined by f of x, and the bottom of the rectangle will be determined by g of x in some way. And there's my approximation. And then what am I going to do? Well, I'm going to see what happens in the limit as I make these approximations better and better by taking the width of the rectangles to be smaller and smaller. Well, this is just a Riemann sum, but what Riemann sum is it? The answer is that it is going to be the sum from I equals 1 up to n of the top of this rectangle is going to be f evaluated at xi star, where xi star is some point in the ith interval here. And the bottom of the rectangle is going to be g evaluated at that same point. And then what I'm going to do is I'm going to take the difference between them, because this is the height of rectangle number I. So the height is the difference between the top of the rectangle and the bottom of the rectangle. And if that seems confusing for a moment, just take a minute to kind of think about how would you find the area of one of these rectangles in general. And then, of course, I have to multiply by the width of the rectangle. Well, the width of the rectangle is b minus a divided by n. It's the difference between the two sides divided by the number of rectangles that we've got. But notice that what this is actually a Riemann sum for f minus g. That's all it is. It's really just a Riemann sum for the function that you get by taking f minus g. And so, in the limit, as n approaches infinity, what we end up with here is actually just, I'm going to have to write this on the next line because I don't have any space. What this is going to be is it's just going to be the definite integral from a up to b of f of x minus g of x dx. And there we go, that's all we've got. So actually, what we can say is to find the area between two curves, we just take the top curve minus the bottom curve, and we do the definite integral. Now again, that may not seem so surprising, but I wanted to show you this thinking through with the Riemann sum idea, because in the future, we're going to start thinking about other types of problems using Riemann sums, and those other types of problems are maybe going to be just a little bit more complicated than the sorts of things that we're seeing here necessarily. I mean, maybe they won't be stupendously more complicated, but there will be problems where the Riemann sums that we end up with are not quite as obvious as this one. And so I think it's good to see how do you reason through this sort of thing in this example for the areas between curves that makes things relatively nice and simple. So let's show an example of using this idea that we just came up with. Actually, first, let's write down what we've said. So the area between x equals a, x equals b, y equals f of x, and y equals g of x, if f of x is bigger than or equal to g of x on the interval from a to b, is the integral from a up to b, f of x minus g of x. So that is what we just proved. As an application of this, let's suppose that I want to find the area between y equals x squared plus 1 and y equals negative x from x equals 1 up to 3. So how would I go about doing this? Well, the answer, and you might want to actually take a minute and try this on your own first to kind of see if you can just do this problem. I need to figure out, first of all, which one of these functions is my top function and which one is my bottom function. In other words, which one is larger than the other one? Well, the thing is that from 1 up to 3, this is always negative. Whereas this is always positive. This is going to start here at 2, and it's going to get bigger. In fact, it's going to get much larger than what this shows here. So we're looking at what is this region here. This is my y equals x squared plus 1. So that is going to be my function that is on top. And this is going to be my function that is on the bottom. So I want to do the integral from 1 up to 3 of x squared plus 1 minus negative x dx. Now, again, this is something that is true back in all the way to algebra. When you subtract one function from another function, we really want to make sure we subtract the whole function. That's why I put this into parentheses here. So that is something to be somewhat careful about when you are doing these types of things. Make sure you subtract the entire bottom function from the entire top function. Don't just put the minus sign and then write the other function, because if there's more terms, you're going to mess it up. All right, so now how do we do this? Well, the answer is this is a reasonably straightforward integral to do. We know how to find this antiderivative. This is going to become x, that's not a 3, x cubed over 3 plus x, and then this is going to be plus x squared over 2, and we evaluate that from 1 up to 3. So then what we can say is, all right, so that's going to be equal to 3 cubed over 3 plus 3 plus 3 squared over 2 minus 1 cubed over 3 plus 1 squared over 2. That is going to be equal to 9 plus 3 is 12. So 24 halves plus 9 halves is 33 halves, and then we're going to be subtracting 3 halves and also subtracting 1/3. So this is going to be 15 minus 1/3. Which is, let's see, 14 times 3 is 42, plus another 2/3, so we end up with 44 over 3, I think. If anybody comes up with a different answer for some reason, email me, because just on the off chance I managed to screw up one of my arithmetic things, I want to make sure that I'm not lying to you guys. But I think I've done this correctly, because, yeah, this would be 15, so 14 and 2/3, 14 is 42/3, and we come up with 44/3. So we've managed to find this area. And that's not too bad. Now, where these kinds of things get a little bit tricky is that you can have problems where the top function and the bottom function aren't necessarily always the same thing, or where we actually don't have the bounds for the integral given to us. So here's an example of another type of problem. Let's suppose that I want to find the area enclosed by y equals x squared and y equals x. And in order to do this, we need to draw what is going on here. Now, often it's useful to draw pictures of these things to make sure that you see what's going on. Y equals x squared looks like this parabola. And it keeps on going, of course, in both directions. Y equals x is just going to be a straight line like this. So here's my y equals x squared, here is my y equals x. Now, what do we mean by the area enclosed? Well, to enclose a region, what we mean by enclosing the region is that inside of that region, you are totally surrounded by these curves. You cannot run away to infinity. Think about being completely fenced in. So if I am in here, I'm fenced in. I cannot get out. If I were over here, I could run off to infinity. So, I could run off to there is no edge of the plane, but I can run off as far as I want to. Whereas if I am in between in this region, I'm completely enclosed by these functions, okay? So that is what we mean by enclosed, the enclosed region. So to find the enclosed region, we need to figure out where these two curves intersect. So we need to know x squared equals x. Well, this is going to happen at x equals 0 and at x equals 1. I picked this as a fairly basic example because I didn't want confusing or complicated arithmetic stuff or algebra stuff getting in our way. So this is a nice simple equation, but that's what we're dealing with here. In a more complicated example, we would just be doing the same things. We would be asking, okay, to find where this region begins and ends, we just need to figure out what are these 2 points of intersection, okay? So same kinds of ideas, even if this becomes more complicated. And on this region, y equals x is actually the top function. So we want to do the integral from 0 up to 1 of x minus x squared dx. Now, that is going to be x squared over 2 minus x cubed over 3 evaluated from 0 to 1. That's going to be 1/2 minus 1/3 minus 0, and that comes out to be 1/6. Sorry, that is a terrible looking 6. That's a slightly less terrible looking 6, I guess. So the area of this region is actually 1/6. Kind of interesting, really, that that's what that area comes out to be. But there we have it. Now, as a similar example, we can think of lots of other kinds of problems like this, okay? So for instance, we could ask, what is the area enclosed by, let's say, y equals x squared, and y is equal to why am I confused now about what curve I want here? So I want this curve to -2x. Let's do that one. That should work out in a somewhat reasonable way. So I'm going to ask you guys to take a minute to think about this example, figure out what the region is, and then do this problem. So pause your video, try this out, and then come back and we'll work through it together. Okay, so hopefully what you did was you started by kind of getting a graphing sense of what's going on with these functions. It's not essential, but it's a pretty good idea usually to do this. So we have our parabola, y equals x squared, and then we have our -2x. Now the -2x is going to go like this, and x squared equals -2x. This is going to have the solutions x equals 0 and also x is equal to -2. So once again, this is a fairly straightforward one to solve the equations, and so that part is fine. So this is going to, we're looking at this region in here this time, which goes from -2 to 0, and the y equals -2x, that is our top function. Now, if you had trouble coming up with this, and you went on without being able to get to this point, see if you can now maybe finish off this problem with the sort of setup that I've given you here and see what you get. Otherwise, let's keep going. We'll set this up and see how this comes out. So we go from -2 up to 0. My top function is -2x, and then I am subtracting x squared dx. So this is going to become -x squared minus x cubed over 3, evaluated from -2 up to 0. I'm afraid I have to erase the setup here because of a lack of space, just to finish this off. So this is going to be -0 squared minus 0 cubed over 3 minus the negative of -2 squared minus -2 cubed over 3. Okay, we have so many negative signs bouncing around here, and I should mention that one of the most common errors that people make, and I don't just mean students, I mean everybody, professors, PhDs, everybody is losing negative signs. It's really easy to do. As an undergraduate, I spent hours in our study office with my classmates. We would do these problems. They would span like boards going all the way around the office. We'd do all the hard parts just fine, but we would end up having to spend hours hunting down negative signs that we'd forgotten or inserted accidentally. And I've read about like high-end research people who get together and spend hours working out problems so that they could double check to make sure negative signs didn't accidentally disappear or appear where they shouldn't. Hopefully, all of my negative signs are correct. These are just 0, so that's fine. This is going to be negative, let's see, 4, but it's negative, so that becomes negative 4. Negative 2 cubed is negative 8, but it becomes positive, so we get plus 8 over 3. Now, 4 is actually 12 over 3, so this becomes negative of negative 4/3, which comes out to be positive 4/3. Okay, so as you can see, in some ways, the setup of this problem, there's kind of the two separate areas where you can mess up on a problem like this. You either mess up because you didn't set it up correctly, like you got the wrong integral or whatever, or you generally mess it up because when you do the integral, you make an arithmetic mistake of some kind, often related to negative signs that shouldn't be there. Little tip, when you're finding areas, the answer should always be positive in this case. Therefore, if your answer comes out to be negative, you know something has gone wrong. You don't necessarily know what, but it tells you should go back and double check things. Hopefully, it's something as simple as you flipped the functions. You accidentally wrote the bottom function as if it were the top function, and that's all you need to fix. Because that's a very easy fix. That just multiplies everything by -1. That negative carries through the entire problem and switches the sign. But maybe it's a more complicated thing than that. Now, one of the problems that we can encounter is that sometimes we can end up with a situation where we have got many different regions involved that are enclosed by a couple of functions. And that's sort of where things get particularly tricky, okay? So let me just illustrate the setup in a particular problem. So how would we set up the integral for the area enclosed by y equals f of x and y equals g of x if this is the picture that we have? So let's say that this is my f of x and this is my g of x. And let's say that this is A, this is B, this is C. So herein lies the problem. Actually, you know what? Why don't we try being fancy here? That's why we're not going to try being fancy, because I don't know where I put my other colored marker. We're going to use a different color for f of x than for g of x so that it's easy to see which one of these things is which. And by the way, again, another little tip here. Okay, this doesn't work, so that kind of takes care of that genius idea of mine. I wonder if one of these others works. Hey, that one works. Having different colored pens and stuff can really be a good idea when you're doing a lot of these problems. So y equals f of x, now in the black color instead of blue so that we can distinguish them. Okay, well, if you don't have colored pens, it doesn't really matter. It's not like life or death here in terms of whether you can solve the problem, but it can help you out. So the way that I would set this up is I'm trying to find the area of this region and the area of this region, but the problem is that which function is on top actually switches in this process. So I actually can't just set up one integral. I'm going to have to set up two integrals, because I'm going to be integrating the integral from a up to b of f of x minus g of x dx plus the integral from b up to c of g of x minus f of x dx. Another way to think about this is really the height of the rectangle in general, it's the absolute value of the difference between f and g. But the absolute value, whether that's f minus g or g minus f, is going to depend on whether we are talking about a situation where f is bigger than g or a situation where g is bigger than f. And so when they start flip-flopping like this, we need to break up our integral into the different pieces, the parts where f is bigger and the parts where g is bigger. And then we can work out these problems without any difficulties, but we do have to be cognizant of the fact that this is something you have to check on, okay? You do have to be a little bit careful about that. So that is just something to keep in mind that you will need to worry about, that when you do this, make sure that you get every single region that is enclosed, and then also make sure that each region that you have, you are going to be able to figure out which function is on top and which function is on the bottom. And give me just a moment while I bring up the example that I wanted. I'm going to pause this for a second. Okay, we're back. Sorry, I wanted to bring up this example, and I didn't think that you guys needed to see the lower half of my face as I was trying to find the notes. So let's suppose that we want to find the area enclosed by the curves y equals 2x cubed minus x squared minus 5x. Wait, did I say minus? Yes, minus. And y is equal to negative x squared plus 3x. Now, if you go ahead and you make a graph of these things, and I'm going to kind of show you what the graph comes out to be, but if you go ahead and you make a graph of these things, what you will see is that you get something that looks like the following. So the picture that you get, and bear with me because again, artistically challenged here, so this is not going to be pretty. But for the x cubed one, you get something that looks sort of like this. It comes up, it comes down, it goes back up again. I am not making this precise at all, so please don't think that this is an exact picture of what this looks like. We don't need exact. What we need is a rough sketch of what we kind of think should be going on here. Now, the x squared ends up doing something like this. And so what we get here is, this is my cubic, this is my quadratic. We end up with these two regions, a region on the left here where the cubic is bigger than the quadratic, and a region on the right here where the quadratic is bigger. So where are these two things equal? Well, if I take 2x cubed minus x squared minus 5x and set that equal to negative x squared plus 3x, the first obvious solution is x equals 0, because at x equals, I can factor an x out of both of those. If we factored the x out, then this becomes 2x squared minus x minus 5 is equal to negative x plus 3. And what is that going to become? So if I start solving this, the negative x's are going to cancel on both sides. And this leaves me with 2x squared is equal to 8, or x squared is equal to 4. So that gives me x equals negative 2 and x equals positive 2. So this intersection happens at negative 2 and this intersection happens at positive 2. Hopefully everybody is okay with what we've said so far about that. So more generally, if I'd had something perhaps a bit more complicated, I may have had to appeal to things like the quadratic formula to solve one of these equations and find the intersection points. When you find these intersection points, any techniques from algebra are possibly fair game for this stuff. And this is one of the things that I think makes Calculus 2 a little bit more challenging, is that at various times we are going to be referring back to all kinds of stuff that maybe you don't remember doing in a while. And so you got to kind of be ready for anything. It's very much this like agility kind of exercise where you jump from one thing to another all the time. Okay, so now, and I should say the other intersection is of course at 0. Well, that's kind of obvious. We said that was 0. So hopefully you guys have this down. I'm going to erase what we've said about this stuff, and we're going to set up the integrals here. So, okay, I didn't mean to erase the actual function. Let me write that down again. It's 2x cubed minus x squared minus 5x. So over here, this region, which we're going to call region 1, this is region 2. So R1, this is going to be the integral from minus 2 up to 0 of 2x cubed minus x squared minus 5x minus negative x squared plus 3x. And all of this is multiplied by dx. So this is going to be the integral from minus 2 up to 0. Let's see, we're going to have 2x cubed and then minus x squared plus x squared. The x squareds cancel. And then minus 5x minus 3x gives me minus 8x. So that actually simplified a bit more than we might expect here. It's not actually as bad as you might sort of fear that it would be, I don't think. And so this is going to become x to the 4th over 2 minus 4x squared evaluated from negative 2 up to 0. And the zeros are all going to cancel out. So this is just going to be negative 2 to the 4th is 16 over 2 minus 16. So 16 over 2 is 8 minus 16 is negative 8. That comes out to be positive 8. So R1 has an area of 8. Okay. Long problem, right? Because we're not even done yet. I've only found half of this thing. But fortunately, one thing that we can say is that when we flip this around, when the quadratic becomes bigger than the cubic, the difference just takes these and flips their sign around. And so this is going to mean that to find R2, this is going to be the integral from 0 up to 2 of negative 2x cubed plus 8x. Give me 1 second here. Somebody is calling me and I don't know what's going on. Sorry about that. My wife was calling, so I had to answer that. So back to where we were. We're trying to find R2, and I didn't put my dx yet. But the point is, when I take the difference in the other order, it just flips the sign here. Now you can carefully compute what is the quadratic minus the cubic if you want to, but it's going to come out to be what we see here. And when we do this integral, well, actually, it's kind of the same integral as we did before. So unsurprisingly, we get something kind of similar. We're going to end up with negative x to the 4th over 2 plus 4x squared evaluated from 0 up to 2. That is going to be negative 2 to the 4th over 2 plus 4 times 4. That's going to equal 8 as well. So R2 happens to be a total of 8. Now, don't expect that this is always going to happen. We got R1 and R2 to be the same. That's kind of, it happens, but it's not always going to be the case. So if I gotten something else that wouldn't necessarily mean that there was something wrong. In this case, they just happen to be the same number. So the total of these areas is 8 plus 8, which is 16. So, long problem, as I said, and that's one of the other things that makes calculus 2 difficult. A lot of the problems that we're going to be doing, they are not short. They are lengthy problems with many steps, many an opportunity to run into an arithmetic error or something like this. So I'm just warning you, be careful when you do this stuff. Don't rush yourself. And remember, break it down into the pieces. Yes, there's a lot of pieces, but each piece is hopefully something that you know how to do, okay? So hopefully you'll be okay with each of the things that you need to do as you go on here. And then you just got to kind of put them together and hope you didn't screw anything up in the process. All right. So that's another example of finding these kinds of things. And of course, you can do this with all sorts of stuff. Now, what if I wanted to find an area that is enclosed, but it's enclosed a little bit differently? Like, what if the curves that I have don't give me y as a function of x? What if instead I had something like the area enclosed by x equals y squared and x is equal to 4 minus y squared? Because the problem here is, what is this region going to look like? Well, it's going to look something like this. X equals y squared is going to look like a horizontal parabola like this. And then 4 minus y squared, well, that's going to look like this. Sorry about that. It takes me a minute to draw everything, as you guys have no doubt observed. So I could do this problem in the same way as we were doing it before, but it'd be kind of complicated, because suppose that I want to write down how to do these regions. Well, if I break this thing up into this piece over here and this piece over here, the top function here would be like y equals square root of x. This would be y equals negative square root x. And then the top and the bottom functions over here in this region, they'd be something else entirely again. Kind of annoying to do it this way. I could do it, but it would be rather long and difficult. There is an easier way, thank goodness, to dealing with this. And that is, let's go back to thinking about Riemann sums. And let's see if there's maybe another way of approximating this kind of thing. What if instead of doing the rectangles as vertical rectangles, what if I make my rectangles these wide, thin strips? In other words, what if I break up this vertical strip into pieces, and on each one of these pieces, I approximate with a horizontal rectangle. Well, when I do that, I'm going to get another Riemann sum. But the difference with this Riemann sum is that the height is now going to be, if this goes from A up to B, the height of the rectangle is now going to be B minus A over the number of rectangles, and the width is going to be, if I think of, and this is not specific to these problems, but if I think of this as my y equals g of x, and this black function as x equals g of y, and this as x equals f of y, the width here is going to be f of yi star minus g of yi star. In other words, we are kind of interchanging the roles of x and y here, because we're using these horizontal strips, and the width of the horizontal strips is the difference between the right endpoint and the left endpoint. It's clearer that there's a left endpoint if I actually draw the rectangle, isn't it? So what we can say is that the Riemann sum that we end up with is a Riemann sum, except it's a Riemann sum with the variables yi star, and in the limit, what I'm going to get is the integral from a up to b of f of y minus g of y dy. In other words, I'm doing an integral that instead of moving along the x-axis, moves along the y-axis. But it's still just an integral, because it is still just the limit of some Riemann sums. And that is another valid technique. If you can write these curves more easily with x as a function of y, that's what you should do. Write x as a function of y, and then use the same formula, but with x and y interchanged. So now you're doing an integral over y's. In this case, then, what am I doing here? Well, let's get a little bit of space here, and let's see where these things intersect. If I want y squared equals 4 minus y squared, this means 2y squared equals 4. That is y equals plus or minus square root 2. So I'm going to be doing the integral from minus square root 2 to positive square root 2 of 4 minus y squared minus y squared dy. And there's my integral. So this is going to become the integral from minus square root 2 to positive square root 2 of 4 minus 2y squared dy. And now all I need to do is to figure out how to do this integral. Well, at this point, you're probably used to doing these kinds of integrals, so I'm not going to actually bother showing you the full solution here. But this is how you set up this integral. And you can use this technique in general. Like I said, anytime that it's easier to give your curve with x as a function of y instead of y as a function of x, then to find the area, you can use an integral over y instead of an integral over x. This is an idea that we're going to return to in the future as well. Sometimes we come up with some quantity that there's multiple Riemann sums that we could use to approximate it. Like, given any region, I can approximate it with vertical rectangles or horizontal like I've drawn here. So it's really just a question of which is it easier to sort of write down? Is it easier to write down heights, or is it easier to write down widths? In the examples we did before, heights were the ones that were kind of easier to write down. In this example, widths are what's easier to write down. We just pick whatever's convenient for us though. So there's kind of this freedom of choice here, and you want to make the smart choice because either will work, but one of them is going to be a lot more straightforward. Okay, so I hope that that has been sort of clear. I know we didn't do a lot of examples here, so please do take a look in your book for more examples. Examples in Calculus 2 are pretty lengthy. This is a class that you're going to spend a lot of time in. Like in Calculus 1, when you're told, oh, you're going to spend 6 hours a week on homework, a lot of people are going to end up being able to get that Calculus 1 homeworks in much less than 6 hours maybe. Calculus 2, not so much. You're going to spend a lot of time reading and on homework. So I strongly encourage you to make sure that you dedicate enough time to actually looking through this stuff because, yeah, these examples aren't short. They're not simple. They're very complicated examples in a lot of ways, at least in the sense of having lots of steps. And yeah, I just want to make sure that you guys, really see a bunch of examples. One more thing, and I'm going to post this in the next couple of days onto Blackboard as well. But if you want even more examples, then a good website to look at is Paul's Math Notes. And he has notes for everything running from algebra through Calculus 2, maybe Calculus 3 even. And I even use his website sometimes when I want to pull up examples for certain things in calculus too, because sometimes I want an example that does a very particular thing, and so sometimes I will reference his website as well in the examples we do in class. But usually you can take a look at his website and get more examples than what you see in your book and in class here. All right, I'll be posting another video in a couple of days. By the way, this stuff all corresponds to like chapter 6.1 in your textbook if you're trying to keep track, and I will see you soon.